The purpose of this video series is to give a casing design overview for anyone who has an interest or is associated with the oil and gas industry. I will try to explain all the important aspects about casing, its design, and application. This video is the first in a series on the subject of casing design overview. In giving this overview, I hope to dispel the myth that casing design is this mysterious and highly technical work product that only a few people are qualified to do or requires sophisticated software. The title page there gives my contact information as well as the notes that I will be utilizing in doing this overview for casing design. I suggest that before you begin this video series on casing design, that if you do not understand the concepts of overburden, pour pressure, and fracture pressure, that you would watch the YouTube video that I recently did and posted. Also the notes for this overburden, pour pressure, and fracture pressure YouTube video that I posted are listed there also for your information. In session one, I intend on discussing the hierarchy of engineering responsibilities related to casing design, the functions of the various casing strings, the primary casing loads that we calculate when we're doing casing design work. I will talk about the casing applications in which the casing strings are being utilized. I will discuss the production fluid gradients and salt loads that can be exposed on the various casing strings. I will discuss selecting casing setting depths and sizes, as well as coming up with a wellbore schematic that is necessary to begin the casing design process. I will also discuss casing manufacturing and properties, as well as casing connections. The remaining series will be some additional topics that go along with casing design. In the next session, I intend on discussing casing design equations, casing design criteria, safety factors that's used in doing casing design work, general procedures for doing casing design, and then the recommended sequence of casing design activity, which is the order in which you should do your casing design work to make it easier. And then in the last session, I will go over casing design examples. I will also go over an exercise about pressure testing of casing during the execution of drilling a well. And then I will end with a explanation about buckling considerations and mitigations to mitigate buckling on our wells that we drill. The hierarchy of engineering responsibilities related to casing design are very important. I've listed them here. The very utmost responsibility of an engineer is always to protect people and to protect the environment. Sure, we want to fulfill some project goal that we have in mind, achieve something, make something, do something, but the overarching responsibility that we always have as an engineer is to protect people and protect the environment. One thing I'll just lead off in saying this is that for all the wells I drilled in my very long career with a major oil company, I probably don't even need one hand, the fingers on one hand, to tell you the number of times that the casing designs that I did were checked and verified by someone else. So what that tells you is an awesome responsibility when you think about the fact that you design casing on this well, which could be a very high pressure well, and you have literally a little city living on top of this well while it's being drilled, which could be 100 to 200 people living on top of it. And as well as it turns out to be a production facility, you could have several hundred people living on top of this for a long number of years. That it's all dependent on the work that you did in designing that well. So it's a very awesome responsibility. So number 3 there, it says it has to fulfill regulatory requirements, which is also true. So we always have to abide by our regulatory requirements that wherever we're operating. And then number 4 there, it needs to meet design requirements and conditions. And we'll be talking about that today. We want to have a reliable and robust design for any reasonable uncertainty that we don't know about the project. We always don't know everything. And it also should satisfy the life of the well requirements, including any intervention or any likely future requirements, such as possible deepening or anything like that that we might be aware of. So, I mean, all of these things would be taken into consideration when you're doing casing design. Very important. Now, here's the functions of the various casing strings. We start off on a well with structural pipe, which is either driven or cemented or jetted in place. It's normally the first casing string that's installed on the well. It may even be installed before the rig gets on location, and quite often on land operations, that is the case. It's also used to establish mud circulation. And very important aspect about structural pipe is that it supports the compressional axial loads of the entire well. So design of structural pipe is a very important. It's the foundation of the well. So there's nothing any more important on a building or a house than the foundation. You have to have a good foundation to support the entire well. It also must withstand bending moments, loads at the mud line due to environmental forces like hurricane waves. If you have a jackup rig that's located, say, in 150 feet of water offshore, you will have a bend when you prepare and evacuate for a hurricane. Most often we disconnect from the well, from the rig when we are evacuated. So you actually have unsupported casing of that 150 feet of water depth plus whatever amount of the structural pipe is above sea level that is going to be exposed to the hurricane wave conditions, and we have to design that to be able to take that bending moment from a wave hitting that freestanding pipe. It also requires design for a buckling load from the lack of lateral support. So we disconnect from that well on a jackup rig, and we cannot have it buckle and fail due to buckling conditions as well. So it has to be designed for a buckling load along with the bending moment from a hurricane condition. And it also has to include the design of the soil strength. So it's not just designing the pipe itself, but we have to design take into account the soil conditions such that when you reach a very, very deep depth, you do not want to get to some point in a well, you've almost TD'd a well, and then have this structural pipe move down hole because it cannot withstand all the loads that have been put upon the soil. Nothing to do with the pipe, but it's the soil conditions are not strong enough around the pipe to support the entire loads of the well. So for this diagram on the right here, this structural pipe would probably be something set, maybe 200 to 300 feet below the mud line. Sometimes on land wells, it's as shallow as maybe 80 feet below mud line, something like that. Then the next string of casing that we would probably set on a well would be a conductor casing. Normally, conductor casing is usually cemented, almost always, and it's probably, it could be the first string of casing for onshore wells. So sometimes we will use the term a conductor casing on a land rig operation. In reality, that conductor pipe is also serving as the structural pipe. So it's kind of a dual role, serving as the conductor pipe for establishing mud circulation, and it is also serving to support all the axial loads of the well. It also may be set and used to mitigate broaching due to a higher mud weight around the structural casing. So if you're going to drill quite a long way before you get to your surface casing setting depths, for this diagram, I just chose 4,000 feet. If your mud weight gets high because you're drilling fast in this interval and picking up all the cuttings in your mud, it would have a tendency to lose returns around this structural pipe. And so you may actually be more economical feasible to stop and set a conductor pipe in order to allow you to avoid the lost circulation as you drilling ahead to your surface casing setting depth. It also may be required due to government regulations or safety to provide additional time to evacuate. So if you say that if something were to happen between drilling between 1,000 feet and 4,000 feet on this diagram, if I've got pipe set deeper than 300 feet, it would give the people on board the rig more time to evacuate should something happen. So that's another reason that we might set conductor casing. It also may provide structural support of axial loads when it's cemented inside the structural casing. So quite often, this string of conductor casing that on this diagram is set at 1,000 feet would be cemented all the way to the surface. So you can actually think of it that you have pipe inside pipe that's cemented together, which makes it very strong, which would also serve to support the structural loads. And then another very important aspect for any of these casing setting depths is going to be required to isolate freshwater aquifers. You know, oil and gas is precious, but fresh water is really precious around the world. So we're always going to set casing strings that will mitigate freshwater aquifers and protect, isolate salt water from fresh water. So that could be another reason we would set conductor casing on a well. It would probably be set all the way through the freshwater aquifers before we hit any of the saltwater aquifers in the earth, in the wellbore. Now, surface casing is, by definition, I call it, is the surface casing would be the first string of casing with BOPs installed on top for well control. So the fact that we install BOPs on some string of casing, and generally speaking, we'd call that surface casing. It's probably the most important casing string to protect people and the environment. It requires the most critical planning and robust casing cementing for well clusters at the surface. If you think about the fact that you're doing a pad drilling, either offshore or onshore, where you're drilling, say, 8 to 12 wells at the same surface location, your integrity of your surface casing is only going to be as good as your weakest, I call it, cement job on any of the wells that you drill. So it's very important to make sure you have good isolation on a surface casing string by paying a lot of attention and doing a good cement job on all your surface casing strings, especially when they're in a cluster, you know, multiple wells located at the same surface location. It is, again, surface casing is usually set at a sufficient depth to mitigate broaching of the well from a well control event for protection of people and the environment. So if you set surface casing at a deep enough depth based on experience in an area, no matter what happens downhole, you may exceed the pressures in the wellbore and have a major well control event in which you lose the whole section below that surface casing, but it doesn't result in anything, I call it on the news. The well doesn't blow out. It doesn't breach around the outside of the casing. So it doesn't make any media event, and it protects people and the environment. So that's why surface casing is so important. It's set at a deep enough depth that no matter what happens, the people on the surface are going to be okay, and it's not going to result in an environmental impact to the surface. It also is going to be set again to a depth to isolate freshwater aquifers. And then for shallow wells with lower axial loads, it also may be designed for the compressional structural loads. So sometimes it gets to be a little bit confusing, but surface casing, the very first string of casing on a land well may be at a very shallow depth, say 200 or 300 feet. And we actually put BOPs on top of that. So that string of casing could serve as the surface casing, since it has BOPs on it, and it also serves as the structural pipe. So it could serve as, I call it, multiple functions. Now, an intermediate casing string is designed to isolate the upper section of the well that is normally pressured. And we'll talk a little bit more about this as we go along. So it's the upper part of the well may be pressured. When we say normally pressured, it's probably a pressure that's fairly close to 9 pounds per gallon, the equivalent mud weight. Once you get to some point in the well and you have to increase mud weight, your fracture gradient does not allow you to increase mud weight. So you have to set a string of casing to be able to increase your mud weight without losing returns. So it's set to increase the fracture gradient when the mud weight required exceeds the surface casing fracture gradient. It also may be used to mitigate wellbore stability or hole cleaning. So for like a long reach well, you may actually set an intermediate string of casing, not that you're increasing mud weight, but just to mitigate wellbore stability because you've got a long open hole section. And it also may be set to mitigate kick tolerance with increasing pull pressures. For example, a 1/2 pound per gallon kick intensity at 10,000 feet would stress a shoe at 5,000 feet to 1 pound per gallon. So it's based on mathematics. So if you had a 1/2 pound per gallon kick, that's double the depth. 10,000 feet is double the depth of 5,000 feet. So it's going to have double the intensity of the stress at the shoe and have a 1 pound per gallon stress at 5,000 feet. And likewise, a 1/2 pound per gallon kick intensity at 15,000 feet would stress the same shoe at 5,000 feet to 1.5 pounds per gallon. So sometimes, we have companies have processes in place to mitigate kick tolerance. So that could be another reason that we might set intermediate casing. And it also could be a regulatory requirement. So there's different reasons that we might set a string of casing, intermediate strings of casing. So now production casing, by definition, is a string of casing that extends the entire length of the wellbore, and it's set to protect and isolate the entire wellbore, and it's used to facilitate completion operations. I mean, it's very common, probably the majority of wells that have been drilled over a long period of time, 60 or 70 years, is they probably set conductor casing on the well that served as surface casing on say a land job out in the middle of the mid-continent USA. They may have set that conductor casing at 300 feet, and then they drilled maybe to 2,500 feet, and they ran production casing on the well and completed a well. So that casing that was used to do all the workovers and change zones and produce oil and gas was called production casing. And then we also set drilling liners quite often. A liner, by definition, is a string of casing that only isolates an open hole section and does not extend to the surface. So we do this for several reasons. A drilling liner is set to increase the fracture gradient when the mud weight required exceeds the intermediate casing fracture pressure. So you could have the case where the intermediate fracture pressure, let's just say, was 16 pounds per gallon. Well, if you start getting to the point that you're weighting your mud up close to 16 pounds per gallon, and you're going to possible lose returns, then you would set a drilling liner on the well in which you would drive up the fracture pressure maybe to 17.5 pounds per gallon, and you could weight your mud up to 16.4 pounds per gallon and drill ahead without losing returns. It's also used to mitigate wellbore stability. Again, quite often as you increase mud weights, it's especially on directional wells. It can also be used to mitigate hole cleaning issues on long reach wells. Is another reason that we will set drilling liners sometimes. And it also can be used to mitigate kick tolerance with increasing pull pressures. You know, as you get deeper and deeper, the mathematics always works when you're evaluating kick tolerance. And then liners are used to mitigate annular pressure losses and increase cost efficiency of well drilling operations. So instead of running the casing all the way back to the top, we just run a short section to drive up the fracture pressures, isolate open hole without spending so much money by running an entire string of casing. And then I did not put this on here, but another reason we run liners many times is if we ran an entire string all the way to the surface, our equivalent circulating density would increase to the point that it could cause us to lose returns just due to the back pressure of having the smaller casings coming all the way to the surface with a drill pipe inside of it. And then sometimes we use that casing string not only to drill through, but we use it as a production liner. So it's a section of casing that's run in the lower portion of the well, an open hole, to facilitate completion operations. So we actually may drill through it and then complete inside of it. So it could be used for both functions. So it's set to isolate the open hole and facilitate completion operations. And it may be used to increase cost efficiency of the well drilling and completion operations by saving the length of casing that we run on the well by only running sections just in open hole, not all the way to the surface. And we also use production liners to retain a larger ID of the production casing above that liner for larger OD completion equipment. So an example with that would be a subsurface safety valve. So we might run, say, 3.5 production tubing in the well, and we only need a production liner that can accommodate the packers and the equipment for 3.5 tubing. And then we want a larger ID up at the top if we're going to have say the OD of the subsurface safety valve is going to be maybe something like 6 inches OD. So we'll retain that large ID to put some safety valves and other completion equipment in. And then we may run a string of casing, tieback string of casing that extends from the liner top in the wellbore up to the surface. So quite often we will have to run a tieback string of casing when our pressures exceed the rating of our intermediate casing and we're not able to complete the well through intermediate casing. We'll have to run a tieback string to drive up and have a larger pressure that will suffice for the ratings that we need to complete the well. And then production tubing is something that's run at the very end of a well, which serves as a conduit of production fluids from some depth down in the well up to the surface. So it's, it could be That production tubing could be run in a liner, it could be run inside the intermediate casing, it could be run in production casing, any of those. Now, our primary casing loads that we will experience and talk about are burst, collapse, and then axial loads. Well, burst loads, it's just simply the fact that the pressure on the inside of the casing is larger than the pressure on the outside. And then a collapse load is that the pressure on the outside of the casing is larger than the pressure on the inside. So in both of those cases, we're going to be talking about differential pressures. Which is the highest pressure, on the inside or the outside? If the highest pressure is on the inside, it's a burst condition. If the highest pressure is on the outside, then it's a collapse condition. And then axial loads are longitudinal tensile or compressional loads along the axis of the pipe. Now here is just an example of a piece of casing that we might use all the time. This one happens to be a 5-inch OD, and I believe it has I think it's, if I recall, 11/16 wall thickness, a little slightly less than 3/4 of an inch. And it's amazing that this is made out of 135,000 yield strength material that has a burst rating of around 37,000 pounds. So when you think of something that's 5 inches OD with 11/16 wall thickness and it's rated to 37,000 PSI, it kind of gives me the impression it's like a cannon that we might shoot, rocket shells out of. It's pretty intense equipment that we use in casing sometimes. Now casing applications, and we'll be talking about these as we start doing casing design examples, is we can design casing either for the drilling condition or we can design casing for a production condition. So a drilling condition means that the casing design loads will be calculated based on the condition of only drilling the well utilizing drilling design criteria. So drilling design criteria is going to be less stringent than production design criteria. And then the production case is that the casing and tubing loads will be calculated based on conditions of a completed well exposed to production fluids and utilizing the production design criteria. So we'll go through examples of both of these during this series to make sure you understand where these two conditions come from. Now, it's very important, and in both drilling loads and production loads, we're going to be using production fluid gradients based on a criteria and doing our casing design. Now, a typical oil that we will use, or I call it utilize, is pretty common, is an oil weight that weighs about 7 pounds per gallon. Now, the specific gravity of 7 pounds per gallon oil, if we divide it by 8.33, which is the weight of a specific gravity of 1, fresh water, then we'll get a specific gravity of a 7 pound per gallon oil of about 0.84. Now, the API equation that relates specific gravity to API is this formula: 141.5 divided by 131.5 plus the API gravity. So it turns out that if we have an oil that's 7 pounds per gallon, which is 0.84 specific gravity, then its API gravity, if we plug into this equation, comes out to about 37 degrees API, which is pretty light oil and pretty typical. All right. Now gas, I call it the rule of thumb that we will use in this video series, is that if mud weight is less than 13 pounds per gallon, then we will use 0.1 PSI per foot as the gas gradient. So 0.1 psi per foot if the mud weight is less than 13 pounds per gallon, which equates also to 2 pounds per gallon. So if you take 0.1 divided by 0.052, you get 2. So gas, if it's less than 13, weighs about 2 pounds per gallon in your wellbore. If it's greater than 13 pounds per gallon, then we'll use a gas gradient of about 0.12 psi per foot, which is about 2.4 pounds per gallon. Now, both of these are done. It assumes gas, which is methane, which basically is your lightest gas you could have almost in a well, would be pure methane, which has a molecular weight of 16. Now, if you're interested where this comes from, I mean, I've done a lot of this in college, and it's derived from the ideal gas law equation that PV equals nRT. So, where pressure is P, V is volume, N is moles, which is also can be represented as mass over molecular weight, would be moles. R is the universal gas constant, which in oil field units is 10.73. T is temperature, degrees Rankine. And then, like I say, M is mass. Big M is molecular weight, which is 16 for methane. So if we take PV equals mass over molecular weight times RT, rearrange it, then density is equal to mass over volume, which is equal to PM over RT. So if you put these values in there, use 16 as a molecular weight, you'll see that you'll come out with these close to these values for in pounds per gallon, 2 pounds per gallon, based on your pressure in your wellbore. Now, another important aspect that was discussed in the overburden, poor pressure, and fracture gradient video that I did was the fact that salt behaves as a liquid at fairly low temperatures, thereby exerting pressure in all directions. So that's the definition of a liquid, is that the pressure in a liquid is the same in all directions. So casing that is set through salt, therefore has an external pressure on it equal to overburden. So you have to remember, on the outside of the casing in salt, the overburden, that is the vertical stress up and down, will be equal to the stress on the side of the casing. So whatever the overburden is up and down on the outside of the casing, that's the same pressure that's trying to collapse the casing to the inside. So we'll have to make sure we take that into consideration when we're doing collapse loads. Okay, now here is I'm going to have to shrink this down a little bit so we can see it. Casing setting depths and sizes are done with the aid of a borehole fracture gradient model presented in overburden, poor pressure, and fracture pressure video that I recently did. There's the link to that video again on here for you. But when you think about how do we do that, we're going to need to have a model and able to do this. So on this example, we're going to set a string of casing somewhere in the well that's going to mitigate just based on experience. So an experience-based depth typically is picked for the surface casing depth. So for this example, which was done, I think I just made it up in 1,000 foot water depth, I chose 5,500 feet, 5,500 feet as the surface casing setting depth. Now, I also have conductor casing set above that, which more than likely would be required because of regulatory requirements. So I'm not going to get into where you're operating and regulatory requirement, but let's just assume in order to mitigate a broaching around the shoe, which I said the surface casing is probably the most important casing string to have. You can have any kind of underground event happen below this depth, but it's not going to affect the surface. So that's very important. So if we have a string of casing set at 5,500 feet and choosing casing setting depths going down, so we will have this red curve here, which represents our pore pressure. Well, if I have a pore pressure of, it looks like here, it's about 9 pounds per gallon at 5,500 feet. The sand fracture gradient based on this is only about, looks like about 12.6 pounds per gallon. I'm not going to try to read it too close. 12.6 pounds per gallon. And the shell fracture gradient looks like it's about maybe 13.8 pounds per gallon. So even though this is really, really important, even though I drill out of that casing shoe and I do a shoe test to something close to 14 pounds per gallon, if I try to weight my mud up and I have a sand that's at 5,600 feet, let's say I have a big old blocky sand that's at 5,600 feet, and I drill down and I get down here to 10,000 feet and I start weighting my mud up above 12.5 pounds per gallon, I start losing mud. There is nothing wrong with the earth. There's nothing wrong with the well. It's just a fact that the sand fracture gradient is less than the shell fracture gradient in the same pore pressure and at the same depth. So therefore, whatever is the weakest rock is going to break, and this sand is going to break. So in order to mitigate lose returns, I have to honor this sand, this green line, which is this sand fracture gradient line. Unless I know there's no sand here, then I have to honor and accept the fact that there may be a sand there. So based on using these two curves, at 5,500 feet, my sand fracture gradient is, like say, about 12.4 pounds per gallon, and I can drill as far as I can until my mud weight gets close to about 12 pounds per gallon or so. And then I've got to stop, and I've shown that by setting pipe at 12,000 feet with, looks like 12 pound per gallon mud. So if I set pipe here, now my pore pressure is close to whatever, 11.8 pounds per gallon. My sand fracture gradient goes up to 14 point, looks like 5 pounds per gallon. And my shell fracture gradient goes up to a little over 16 pounds per gallon. So I do the same thing again. I'll drill out that casing shoe. I'll get a shoe test of 16 pounds per gallon, but I start drilling, but I can't drill any farther than my mud weight gets to the sand fracture gradient limit based on where I have sands in that wellbore and what the pore pressures are and what the sand fracture pressures are in that wellbore. So if I have a sand right below that shoe, it's going to be about 14.5 pounds per gallon. And there's nothing wrong. It just means to, in order to mitigate lost returns, I can't go any farther in my well with and increasing my mud weight than whatever this limitation is. So in this case, I stop at 15,500 feet. I set pipe with, looks like about 14.3 pounds per gallon or so mud. And now I have my fracture pressure in the sand goes up to about 16 pounds per gallon. Fracture pressure in the shell goes up to about 17 pounds per gallon. And then I do this again and again. I'm not going to repeat the bottom two strings of casing, but you can see the process. You start at the top, basically, with your surface casing setting depth, and then you choose casing setting depths as you go down to mitigate loss of returns based on the sand fracture gradient. So casing setting depths are chosen to mitigate loss of returns based on the lowest fracture gradient in open hole, which are your sands. And then casing design is based on the maximum fracture gradients of the strongest rock. So, because sand intervals may be faulted out or simply just don't exist in a particular geological section. I've drilled many wells that we thought we were going to experience the sand in an open hole interval, and it just simply was shelled out or faulted out and just didn't exist. So When we do casing design, we ignore the sand fracture gradient line. We do it based on the strongest rock, but we choose casing setting depths to mitigate loss returns, and we do honor the lowest rock strengths when we're choosing casing setting depths. So again, I'll just reiterate this. Casing setting depths are chosen from the top-down method, starting at the top for the surface casing, and then setting the number of strings as necessary to reach TD. Once the casing setting depths are selected, then the sand fracture gradient curve is not required for the casing design load calculations. We're going to do it based on the shell fracture gradients after that. Now, casing sizes are selected based on a bottoms-up determination. So the bottom casing size is chosen based on a completion or drilling size requirement. And then the sizes above must be larger to accommodate drilling and casing requirements. So let's just say for this example here that if this string of casing at the bottom for completion were to be 5-inch, let's say a 5-inch liner, production liner was acceptable, then you start from the bottom. This might be a 5-inch size. This size at 17.5 might be 7-inch. The casing at 15,500 might be 9 5/8. The string of casing at 12,000 feet might be 11 3/4. And then the string of casing at 5,500 feet might be 13 5/8 casing. So you start at the bottom and you go up with sizes that allows you to drill the well based on your wellbore conditions. So ultimately, we want to end up with a schematic once we've chosen casing setting depths, and we put all of our information on our schematic with our pore pressures, our mud weight, our fracture pressures, which are shale fracture pressures, and our TVD depths. So this is what we have to get to before, when we start doing casing design work, we want to get to the point that we understand our drilling environment before rig gets on location, and we lock down this technical work with a I call it a mental picture with pore pressure, mud weights, fracture gradients, setting depths that we're going to do all of our well design work from. Very important. Now, casing manufacturing is interesting. You don't have to know everything about casing manufacturing in order to do, let's just say, casing design necessarily, but it's very, very helpful. If you look at the specifications for casing manufacturing, many of them came about from API best practice documents that were written many, many, many years ago, and common casing sizes here on this chart. I'll just show one. Just say, for instance, like N80 casing. API high strength N80 is an API equation which has a minimum yield strength of 80,000. It has a maximum yield strength of 110,000. So that means in order for an API facility to manufacture casing, it has to be between 80,000 yield strength and 110. Pretty wide range. It happens to be 30,000. Now, the manufacturers of casing, they don't want to have any failures. I mean, they're making casing to sell. It costs them money if they have something that doesn't pass inspection. So more than likely, I've never worked in a casing manufacturing facility, but you can guess that they're probably going to make it sort of right in the middle, around 95,000 yield strength. So that gives them 15,000 yield strength on the low side and on the high side. That way they would not have any rejects in manufacturing their steel. So it would be, quite a bit above 80,000 and quite a bit under 110,000. So it's that's the way they manufacture it. I'm not going to go all over all of these others, but you can see the range on here, and you can look them up in API books. Now, the yield strengths Ranges are listed in manufacturer's table that I just described above. Now, casing is composed primarily of iron, which is a crystalline structure. So it gets its properties from a combination of the materials, the makeup of the steel, and the heat treatment process. It's very much an art and experience-based process. So when you're talking about a crystalline structure, it's a lot like baking bread. So I'm just going to use that as an analogy, that if you're baking bread, the technique in which how long do you let it rise, how long do you cook it, and so forth is very important. So it's a lot of experience goes into the manufacturing process, since it's a crystalline structure. You've got to let these crystals form in a manner that gets the properties that you want. So the heat treatment process creates the crystalline structure, which gives steel its strength and properties. So here's some terms that you probably won't necessarily remember, but you can look them up. Normalized means that the steel is heated to 1600 degrees Fahrenheit and then air cooled. So that's what normalized is. And then it's quenched, means it's heated up to 1600 degrees Fahrenheit. It's held at the temperature for a period of time, and then it's rapidly cooled to 200 degrees Fahrenheit in either water or oil. And then it's also tempered. Tempered means it's heated to 1050 degrees Fahrenheit and air cooled to ambient temperature. So getting this crystalline structure, which gives you the properties of your yield strength, is based on this heat treatment process, the way it's an experience-based process. So this brings about a safety issue that everyone should be very much aware of, and I talk about this every chance that I can in our world that we operate in, is that from a safety standpoint, we should never allow welding or external heat to be applied to any pressure or structural member without proper design. I'll give you an example of that. Let's say the derrick leg. The derrick leg may be built out of high strength steel. If the mud engineer walked over to you and he wants you to weld on the side of the derrick leg I call it a bolt, in order to hook his handle for something that just makes it handy for him, you don't do that, because you could change the properties of that steel. Nothing happens right then and there. So in other words, you do that welding on there, nothing happens, but then 6 years later, something is going on and you exceed the yield strength, that leg fails, and it's a catastrophe. So you just don't do that. So this stop work authority should be utilized immediately before welding or heating on anything that holds pressure, like a pressure tank or a structural member. Just don't do that. The yield strength of the material could be altered, causing a catastrophic failure in the future. So that's a no-no to do that sort of thing. If you're gonna do a proper job of that, then you're gonna have to go back, and then you have to renormalize it, quench it, and temper it on location, which can be done, but it has to be an engineered process. Now, another property of casing is the wall thickness. The API tolerance for wall thickness is actually 12.5%, which means that if something was supposed to be 1 inch thick, it actually could be 0.875 inches thick, and it would pass API. Now, this minimum wall thickness of 0.875 is based on a very old manufacturing capability of greater than 50 years ago. And that was obviously before computer controls, and it was also for thin-walled casing. One of the most common casing sizes and weights of casing that has ever been run is 8 5/8 casing with a 0.264 inch wall thickness. In fact, I put the specifications for that down here. That was pretty typical uh, surface casing for, I'm gonna call it thousands of wells, like out in the mid-continent US and West Texas, where they would set 8 5/8 casing, surface casing at 500 feet, and then drill to TD and run production casing. So that's probably the most common casing size that has ever been run if you did it in terms of footage. So if you take 12.5% of a wall thickness of a 0.264, it turns out that's a 0.033 inch variance, which actually is pretty small. I mean, relatively speaking, that's pretty small, and it's based on no computer controlled, very thin walled casing with the manufacturing capability. Now, it's common today to have casing sizes and weights with a wall thickness of 0.625, sort of like this piece of casing is. This one is 11/16, so it's almost 3/4 of an inch thick. All right, so if you take the percent variation of 0.03 inches relative to a 0.625 wall thickness, that comes out to only a 5.3% variation. So if the manufacturers can really make a variation of only 0.033, and you relate that to casing that has a much thicker wall thickness, 0.625, that reduces this tolerance really down to almost like 95% wall thickness almost. So lower tolerances can be easily manufactured today with computer controlled equipment and so forth. Actually, ranges today, we will manufacture and request 90 to 95% wall thickness, and then 95 to 100% wall thicknesses are commonly manufactured and then qualified through inspection processes. So it's actually very common, especially on very thick walled casing, to make casing that's, I call it, between 95 to 100% wall thickness. Another consideration that you need to be aware of is that casing, the outside diameter, if it's for casing that is greater than or equal to 4.5 inches in diameter, can be 1% oversized. So let's say if it was 7-inch casing, 7-inch casing can be 1% greater OD than 7 inches. And then if it's less than 4.5 inches inside the tubular size, the variance is 0.031 inches. So I'm gonna put notes here on you for your information that you need to be aware of. So like I say, example of 11 7/8 casing, which is obviously greater than 4.5 inches. 11 7/8 times 1.01 equals 11.99. That's acceptable. It passes API. There's nothing wrong with it. But something you need to be aware of, if you got casing and it has been manufactured to sort of the high side of API acceptability, then you need to ensure that your casing slips are compatible with the actual casing manufactured OD. It's always a good thing when you start a well, or the beginning of starting a well, is go caliber some of the joints that you're going to be utilizing and pick out some joints. Make sure your casing slips are compatible with the casing, actual casing sizes that's been delivered for your well. Chemical composition is another attribute of specifications of casing. As I've already said, the makeup of the steel along with the heat treatment process is what gives up its properties. Carbon limitations improve the steel quality in general, but we also can add some other high-end molybdenum and other metals to the steel to give it actual properties. I'm not going to get into that in this video. We also have length ranges. Like, we can have joints of casing that's between 25 and 30 feet long. We can have joints, between 30 feet and 45 feet long. So we want the length of the joints manufactured to be compatible with our operations. Some of our rigs can handle different length joints easily in the derrick, and you want to make sure you order pipe with the right length ranges for your operation. Now drift, that's a property, the ability to pass a fairly long gauge, which is close to the ID of the tubular. So you have to make sure that the pipe is made and drifted such that you could run fairly large tools through that casing ID. So that's a standard practice for the manufacturer of casing. Now here are some other terms that you just need to be aware of. Ovality is how round is it? You know, because the reality is it could be made somewhat, and I've exaggerated it on my drawing, but oval shaped. So if casing is oval shaped, it's going to cause different problems of either drift, or it's going to cause a problem with collapse resistance or other things. There's API properties for ovality, but the most important thing I'll probably say about is that in today's time with computer controlled manufacturing, today's casing can be made to much better tolerances than the old API standards of 50 years ago because of the manufacturing processes. So casing today can be made more round. And then the next one here is eccentricity, which means do you have thin spots on one side and thick spots on the other side? So you want, in other words, you want the hole to be in the center of all the steel. I mean, that's in essence, that's what you want. You want it to be same wall thickness all the way around. And then the last bullet point here is high strength casing is when the casing is manufactured to a more stringent specifications than the API tolerances. And those more stringent specifications, it could be for yield strength, it could be for the eccentricity, it could be for the ovality, it could be for the better chemical composition. For many reasons, a particular mill may make better quality of steel than API because they've got computer controlled equipment. They have better controls on the pouring and the furnaces of making the steel itself. They keep all the contaminants out, and they just make a very, very high quality product. Which all of that, they do that, and then they may rate their casing above the rating of API because they're using a higher standard than API. So it's okay, and there's nothing wrong with it. So here's another typical casing property list that I just kind of want to go over. It has, I'll just mention one here. Let's just say we look at P110 casing. So we look at 9 5/8, 53.5 pound P110 casing, has a collapse resistance of 7950. And then here are your internal yield pressure values, which are another way you'll see. Sometimes you'll see tables listed with yield, internal yield. You'll see them with burst. So all of these is really saying the same thing. It's the burst property of the pipe. In this case, the plain end pipe is rated to 10,900. They also give the rating based on 2 API connections, LT and C, long threads and coupling, and buttress, BTC, buttress threads and coupling, and both of them are rated to 10,900, which is equal to the plain end pipe. And then, now one thing you do have to watch, or you should watch, is that sometimes these ratings of the connections are less than the plain end pipe. You actually have to use the lower rating of whatever is specified. So if your connection is rated to a lower pressure than the plain end pipe, then you would need to use the rating of the connection. Sometimes it's the other way around. Sometimes the plain end pipe has a lower rating than the connections. Again, you use the lowest rating of whatever is shown for that material. And then you get over here and you have joint strength. The joint strength for plain end pipe is 1,422 kips, which is 1,422,000 pounds in tension. The Buttress is rated higher than the plain end pipe, and the body yield, I said that wrong, excuse me. This is LT and C. The LT and C casing is rated 1,422,000. So LT and C, which is long threads and coupling, is 1,422,000. Buttress is 1,718,000. Plain end pipe is 1,710,000. So if you happen to be running buttress casing, the number you would use would be 1,710,000, which is less than this value. If you are running LT and C casing, the value you would have to use would be the lowest value, which would be the 1,422,000 for your tensile rating of the pipe. All right. Now, also want to bring your attention to API. This is your ID of the pipe, 8.535. The API drift are these numbers, and then these are special drift, long star steel in this case drift, that many casing sizes, because of the better manufacturing processes, they can make casing that has better quality than API. So for some common sizes that we run, if you ask for, like for 9 5/8, 53.5 pound, you can request an 8.5 inch drift. For 10 3/4, 45.5 pound foot casing, you can request a 9 7/8 drift. And then for 72 pound, 13 3/8 casing, you can request a 12 1/4 drift. So if you will request that, when you place your orders, you can get it. But if you don't request it, and you look at this casing and you've ordered it and it's been delivered to you, it may not be a 12 1/4 drift if you did not ask for it. So these are common sizes that you need to make sure you ask for. Now, casing connections, there's many different types of connections, which I'm not going to cover in detail for this overview, but I do want to share a big improvement in a manufacturing capability that occurred in my career. Connections have to be robust in order to handle the tension or compressional loads, high pressures, bending loads, bending moments, buckling loads, and retain good mechanical integrity. You know, the earliest oil field connections were only a tortuous path of helical threads containing pipe dope that prevented leakage up to a degree. So they were like 8 round threads that had pipe dope in them. No metal to metal seal, no premium connection. Now, with ultra high pressures, we need premium connections that's rated up to 20,000 PSI. Now, what's happened in my career is that computer controlled, precise manufacturing has enabled this capability during my career. Connections can now be cut such that the stress load on the metal to metal sealing surface is very predictable and reliable based on the torque that the connection is made up to, without damaging the connection by exceeding the yield strength on that metal to metal face. So the metal to metal surface is stressed to a high value, significantly higher than the operating pressure, but less than the yield stress, thereby not damaging the connection. So let me kind of give you an example of that. So here on the left, I'm not a very good artist, but I try to draw, and this is something that we're all familiar with, but we probably don't think about it every day, is a flange. When you think about a flange, it's a metal to metal surface. So we have a ring gasket goes into this flange, and then we tighten a bolt through here, which puts a stress on these metal to metal surfaces here, that if we tighten the bolts up to the right torque, we may create a stress on this face of this ring gasket, say to 60,000 PSI. So if we've created 60,000 PSI stress on these face, and it's going to be operating with 15,000 PSI, 15,000 PSI will not leak past 60,000 PSI. So that's the way it works. We've created a stress greater than the pressure that we're going to be operating, which is 15,000 pounds. So therefore, it's not going to leak. So a premium connection, the way it works is you've got threads profile, which is a helical threads cut, and you've got a, if I can zoom this in, we might be able to partially see it. You've got a metal to metal sealing surface down here at the bottom, where it is a very pristine angle cut in this box, and there's a pristine angle cut on this pin that screws into it. And what has enabled this to be successful for our industry is that when you make up this connection to a certain amount of torque, it has installed, if you want to think about it that way, it has installed a stress of, say, 60,000 PSI on this metal to metal surface that's made out of P110 material, and it has not damaged it. So if, in order to be able to make this up and break it out without damaging it, we have to have good quality control on the torque value that predicts with a certain amount of torque we put into this pin when we make it up, that it does put high enough stress on this metal to metal seal to be an effective seal, but yet not go over its yield strength and damage it and galled that into that connection. Because if you damage it, then it's got to be recut and costs a lot of money, a lot of shipping, a lot of problems. So computer controlled integrity of cutting these threads pristine, and these, I call these metal seal surfaces, has allowed us to do this. Now, it's convention by industry that if we're operating less than 5,000 PSI, we can use non-premium threads. So we can use like buttress or 8-round for lower pressure sections of the wellbore. So we might use them, say, down through surface casing. But then everything below surface casing, if we're going to be operating greater than 5,000 PSI, and this is just normal convention, we will use a premium thread. So premium thread, again, is one of those threads that has a metal to metal sealing surface that is extremely good. I call it for pressure ratings, and I call it and not having leakage. Also, it's very wise idea to just making everyone aware of this. It's highly recommended to use square shouldered or wedge type connections to be utilized for the compressive loads up in the upper sections of the wellbore. So you remember, like your surface casing or upper part of the surface casing or conductor casing or structural casing that's going to be in compressional loads, that's going to have to hold up all the weight of all the casing strings run on that entire wellbore. You would want something that has a very robust mechanical integrity, like some square shoulder type connections or wedge connections in the structural, for those structural compressive loads.